This third example provides another illustration of how the dot product can be used to resolve forces into directions parallel and perpendicular to a direction of interest. In this case, we have a bead with a hole bored through it. The bead is mounted on a straight rod and is capable of sliding along the rod, but cannot be pulled through the rod. A cord is attached to the bead and is in tension. Unless the cord is aligned perpendicular to the rod, some portion of the cord tension will tend to cause sliding of the bead either towards A or B. For the particular numbers given in this figure, we would like to know how large this parallel force is and whether it tends to move the bead towards A or towards B. For the purpose of our calculation, we will define the positive direction as being from B towards A. This is completely arbitrary, but it gives us a reference direction. We can see the coordinates of A and B in the figure, so a relative position vector from B to A and its associated unit vector UBA can be defined. We also know how far C is from B, so we can define the coordinates of C from the coordinates of B plus the distance from B to C on the unit vector that points from B to A. And we might also note that there's no distinction between the unit vector that points from B to C and the unit vector that points from B to A because this is a straight rod. Once the coordinates of C are defined, we can define the relative position vector from C to D and its associated unit vector UCD. Then the force component parallel to BA can be defined from F parallel equals the given tension on the unit vector that points from C to D dotted into the unit vector from B to A. If this number turns out to be positive, then we know there is a component of cord tension trying to slide the bead from B towards A. If it turns out to be negative, then the force component is trying to slide the bead in the opposite direction, from A towards B. Let's now carry out the details. First, let's make a note of the absolute position vectors we can see in the figure. We have RA is 18I plus 16K centimeters. RB is 4J plus 4K centimeters. And RD is 15I plus 17J centimeters. We need to find RBA, which is RA minus RB, and that's 18I minus 4J plus 12K centimeters. If we take the square root of the sum of the squares, we find that the magnitude of RBA is 22 centimeters. And then our unit vector from B to A, which is RBA divided by its magnitude, after canceling out a common factor of 2, we end up with 9 over 11I minus 2 over 11J plus 6 over 11K. We said that we would find the position vector of C from the position vector of B plus the distance from B to C on the unit vector from B to A. And the distance from B to C was 11 centimeters. So we have RB, which is 4J plus 4K centimeters, plus the 11 centimeter distance that's given in the problem statement on this unit vector that we've just found from B to A. And that ends up giving us the position vector of C is equal to 9I plus 2J plus 10K centimeters. We can then find the position vector from C to D as RD minus RC. And given the position vector of D that we listed previously as 15I plus 17J, this difference ends up being equal to 6I plus 15J minus 10K centimeters. The magnitude of RCD is the square root of the sum of the squares, and that ends up being equal to 19 centimeters. So our unit vector from C to D ends up being 6 over 19I plus 15 over 19J minus 10 over 19K. Our parallel component that we're seeking was the tension that's given as 380 newtons on the unit vector from C to D dotted into the unit vector from B to A. And that ends up giving us 380 newtons. First term is 6/19 times 9/11. Then we have plus 15 over 19 times minus 2/11. And then finally we have plus minus 10 over 19 times 6 over 11. And if we put all that together, we get that F parallel is equal to minus 65.5 newtons. The fact that this number is negative tells us the parallel component of the force is acting opposite from B to A, so a component of the chord's force is trying to slide the B from A towards B. Finally, in our last example, we have a communications tower that is supported by 3 cables in tension. The tension in cable DA is not aligned with the axis of the support anchored to the ground. The component of that tension aligned with ED acts to pull the support directly out of the ground, while the component perpendicular to ED exerts a bending moment about base E that tries to turn over the support so that ED lies flat on the ground. We would like to know the force components in both directions, parallel and perpendicular to ED, so that we can compare them with failure loads for their respective failure modes. We already have the position vector RED, so we can find its magnitude from the square root of the sum of its squares, and that turns out to be 29.07 inches. So the unit vector aligned with ED can be calculated as 0.344I plus 0.447J plus 0.826K. The scalar component of the force F aligned with ED is F parallel equals F dotted into unit vector ED, which is minus 0.8 times 0.344 minus 2.2 times 0.447 and plus 6.3 times 0.826. And that number turns out to be equal to 3.945, and the units are kips. To get F parallel vector, we take that magnitude and we place it on the unit vector aligned with ED. So that's 3.945 kip times this unit vector of 0.344i plus 0.447j plus 0.826k. And those numbers turn out to be 1.357i plus 1.764j plus 3.259k. Again, kips. The magnitude F perp is the difference between the magnitude of FDA squared and F parallel squared. And it turns out that if we were to find the magnitude of FDA from the numbers given, the square root of the sum of the squares, that turns out to be 6.721 kip squared. So we have this minus 3.945 squared, and magnitude F perp ends up being equal to 5.441 kips. And then finally, if we want vector F perp, we can get that by subtracting F parallel vector from the original FDA vector, and that number turns out to be equal to minus 2.157i minus 3.964j plus 3.041k kip.